of critical eigenvector. This is the point of the 2 points of the discussion in the first hour of our lecture. Okay, so what I mean for free time response. Remember that we have studied in general this problem like this. I am compacting the problem in Laplace domain slash stability analysis, and by taking the determinant of this matrix, putting this equal to 0, we have 4 poles like this, and this is the standard first step of eigenanalysis, and the standard second step of this analysis. We have to solve the following problem. I prefer to rewrite this because I want to be extremely clear with you on this 2 points. And so we have this is applied to W tilde n equal to 0. And then we can evaluate the eigenvector. Okay? So, in the stability analysis, in general, we evaluate these poles and eventually this vector as associated to our eigenproblem. This is one of a possible eigenproblem of your life. And this is the eigenproblem for solving the time response of a linear system. In this eigenproblem, we can ensure or study the stability in the sense that we can evaluate this 4 quantity, 1, 2, 3, 4, which are the poles of our system. And they are, for example, in a case of stable, damped, panel flutter, one here, another here, and another here. So 4 poles. This is for lambda assigned, lambda bar. So we are considering a 4 condition. The system is stable. I know very well that if I increase lambda with an eigenvalue, probably the system will become unstable, but I don't care. Now we are in a stable condition. So we have evaluated this quantity here as S1, and this other S2 here, and this S2 is equal to S1 complex conjugated, and this is S3, and this is S4, and also S4 is complex conjugated. Note that, please, this is important. We have a system with real coefficient. When you take this determinant, you will obtain a characteristic equation with real coefficient. Therefore, your roots are necessary real or complex conjugated. And in general, if you consider structure only system with 0 lambda, you have pure imaginary complex conjugated on the imaginary axis. When you have the damping, this move on the left hand side. If you increase lambda, this we discovered yesterday that this moves the pole coalescence or maybe not a coalescence and so on. But now I want to focus on time response. For for building the time response in the free condition, my statement is the following. The free time response is the combination, is the linear combination of 4 elementary time response. What I'm saying is the following. The time response in this case is the linear combination from n going to from 1 to 4 of Cn, the coefficient of this combination, the eigenvector evaluated, and this exponential, e to the power Snt. So I have this elementary solution, okay? And so please consider that this Wn is a vector. Is this vector here. W tilde is this vector here. Please distinguish this W as a function of t with this W tilde n. W tilde n is a vector of complex number, period. And what I am stating here is that the general time solution is a combination of this vector by this. First comment. The 4 eigenvalues are complex conjugated. If you put a complex conjugated number here, instead of S square, S, you have obtained here a complex matrix. And the eigen solution, the non-trivial solution of a complex matrix is a complex vector in general. So you expect to have W tilde n as a complex vector of complex number. So you expect complex eigenvalues or complex exponential characteristics exponential, excuse me, and so you expect complex eigenvector W in general, but you expect couple of conjugated poles, and correspondingly you have to expect complex conjugated eigenvector, okay, as well. And therefore here in this combination you have, for example, C1 W tilde 1 by e to the power S1t plus excuse me a second, I can, it's very incredible. Okay, it's outside. Okay. We have people singing in, you have people singing, and therefore it's very strange. Excuse me. And so you have C2 double, this W2, if S2 is conjugated of S1, therefore, consistently, this is very easy to demonstrate, W2 is the conjugated of W1, okay? Necessarily, because you can take this equation, if you take the conjugated of all these equations, if you take the conjugated, a huge conjugated, like here, look, you can apply the rule that the conjugated of the product is the product of the conjugated. So, and you have a matrix product with a vector, you can apply this rule as well, and therefore, if you take the conjugated of this, you obtain that the same system is satisfied by the conjugated of the pole with the conjugated of the eigenvector, necessarily. Okay, so we have also couple of conjugated eigenvector. So we have this here plus this here conjugated, which is the second eigenvector, e to the S1 conjugated by time, and the other two. The other 2. Ta-ta. And therefore, I can expect that a result of this combination is a real quantity. So do not be dispirited because you are treating with a complex number. Hopefully your combination will give you a time function, okay? And what about this constant C? The constant C should be complex as well. So in this specific problem, we have, remember, we have our differential equation. I don't want to rewrite this equation. Second time derivative with the damping, time derivative plus the stiffness. This is the problem in time. So you have a mass, damping, and stiffness, and this stiffness is aerodynamic and structural stiffness. And you have initial condition for W. You know the vector W at the beginning as W0, and you know W dot at the beginning of time, and you know this initial velocity vector like W dot 0. So these two vectors here are known. And therefore, if you write your problem in this way, W time is equal to summation of Cn Wn. This can be written as the following. You have by Es and T, okay? This can be written in this way. You have the first eigenvector in column by E to is 1t, first column. The second column E is 2t. The third and the fourth and this is a 2 by 4 matrix, and you can apply this matrix to this coefficient C1, C2, C3 and C4 vector. You can do the same for the velocity. And here you have clearly the Cn by Sn, W and e to the power Snt, 4. And this can be written in the same way, but for column you have W1 S1 e to the power S1t, the second eigenvector, tilde eigenvector, excuse me, tilde S2 e to the power S2t, and please write the same column with for 3 and 4 and apply this to the coefficient C1, C2, C3, C4. Next, please, evaluate this equation for at t equals 0. At t equals 0, you have that W at 0, and you know this vector very well, is equal to, note that this exponential are 1 equal to 1 at time equal to 0, okay? So you have only the eigenvector in column, and therefore you have first eigenvector, second eigenvector, third eigenvector, and the fourth one as applied to C1, C2, C3, C4, and you have the initial condition of the velocity as equal to, in this way you have the eigenvector 1 by S1, the eigenvector 2 by S2, the eigenvector 3 S3, and finally the eigenvector 4 S4 by the same coefficient C1, C2, C3, C4. Now, how many equations we have here? 8 equations. We have, excuse me, 4 equations, excuse me, 4 equations. Okay? And we have 4 equations, and we have 4 unknown. The unknown are these 4 complex number, and C1, C2, C3, C4. So you can recast this system as a linear system of type, for example, like this, where B is W0 and W dot 0 is an 8 by 1 vector, and you can define this A matrix by this. Note that you have 4 equations and 4 unknown. These 4 unknown are 4 complex number. Please, I would have your attention at this point. We have 4 complex number to be evaluated by the knowledge of our 4 initial conditions. But the 4 initial conditions are real number. The C1, C2, C3, C4 are complex number. You can imagine so 4 complex number are determined by 8 parameters, 8 real parameters. Because we have a real part and imaginary part for 1, a real part, imaginary part for 2, and 3 and 4, okay? So one could ignore this point and say, okay, I don't care. I want to solve this linear problem. I know that this is real. What is it? I know that this is real because this is representing an initial condition, but this is complex. And probably this, when I invert this complex matrix for obtaining x, x is real. No. It's okay. And when I will invert this complex matrix, I will obtain potentially a complex value for x, because x, which is represented by this 4 constant, is equal to a to the minus 1 applied to b. And this is complex, and this is real. So, what do you expect to obtain here? And here you have 4 information. On the right hand side, in B, you will have you have initially 4 real information. For obtaining 4 complex information, this is strange, because 4 complex information implies 8 real information. But the structure of the problem you have implemented, you originally obtained this object by a real coefficient analysis, is such that you will obtain the 4 complex number C with complex conjugated pair automatically. So the C2 should be the complex conjugate of C1, and C4 again will appear as the complex conjugate of C3. Okay? And so at the end of the story, the essential real parameter for determining C coefficient are four, which is the real part, the imaginary part of C1 and C2. C2 eventually has an imaginary part which is the opposite of C1, and real imaginary part for building C3 and C4, which are again a complex conjugated, two complex conjugated numbers. So you can determine C coefficient as X coefficient like equal to this A matrix. This A matrix is obtained easily by putting the two matrices here and here, one on the other. Look this representation. Look this colored representation. This is a matrix. This is a 2 by 4 complex matrix, and again this is a 2 by 4 complex matrix, and here you should have this and this, and this final matrix here is to the -1 applied to our initial condition. And this is the way for obtaining this four coefficient. If you have this coefficient, put here, and you have the time solution. Okay, this is a standard way for building your free response, and if you include your C coefficient in this expression, you will have an analytic. Well, once you have determined this, you have an analytic form for expressing this through a strange matrix, function of time, applied to the initial condition. Do you know the name of this matrix? Transition matrix. I knew. Okay, so we have essentially determined our transition matrix by using an associated eigenproblem. The structure of this matrix is depending on W tilde vector, excuse me, I forget tilde, W tilde vector, and the pulse Sn. So this is also known as the eigenform of the free response based on the eigenvalues problem. This is a very well-known issue in dynamical systems theory. Okay? Okay, so this is the first point I promised to you, free time response. Okay? Free time response. Now I want to give you the second point, the role of critical eigenvector. What is the critical eigenvector? I don't know. Critical eigenvector. When I solved this problem, with s squared blah 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 s by blah 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 lambda minus lambda, and the other, this is 1, this is for 2. When I saw this problem, for S equal to Sn, I can determine an eigenvector Wn, right? First component, tilde, first eigenvector, and nth eigenvector. Second component, in the sub-index, I indicate the component. In the super-index, I indicate the eigenvector. Always in my life, always. This is a Mastroti convention. Okay? Sub-component, super eigenvector. Okay? Now, what's happened when we are in lambda equal to lambda critical? In this way, we have the following. We have a couple of poles just here. Here we have S equal to plus J omega critical, or flutter if you prefer, omega flutter. And here we have S equal to minus J omega critical. The other two poles are one here, for example, stable, and the other here. Okay? So, when you put the this value for lambda, you obtain these 4 poles, and you obtain correspondingly 4 eigenvector for building your free solution, for example. And correspondingly to this pole, we have an eigenvector that I want to call critical eigenvector. This is a critical eigenvector because it's corresponding to the critical eigenvalues crossing eigenvalue. Okay, and therefore I have a special vector. The special vector should be composed by 2 complex numbers because it's a complex vector. So, for example, these 2 complex numbers could be 1 plus 0.5j and 31 plus j7. What are representing these 2 numbers? This is my point. Are special numbers the component of the critical eigenvector? What are representing? This is my question. And this is the role of the eigenvector. This is a very interesting point in elasticity. Everybody knows the eigenvalues, the critical eigenvalues in elasticity, but very, very few people are clear the concept of the corresponding critical eigenvector. Povero vettore, così trascurato. Okay, in order to give a role to this quantity, I want to recall to you the following. The solution. The solution, the final solution, is of this type. And I have in general W1, function of t, by the sine pi x by L, plus W2 by the sine 2 pi x by L. And I'm recalling that I have a mode shape here, like this, and I have a mode shape here, like this. When I say mode shape, I'm talking about structural mode shape, of course. The good part of the operator of the plate, the structural part associated to conservative force. So the solution is a combination of time function multiplying these 2 shape functions, this and this. Okay, now what happens in the case of critical condition, marginal condition like this? What happens in this situation? Okay, in this situation, I have exactly what I have written before. In this situation, I have the free response is the free response giving W1T and W2T as equal to, I should have C1, which is the coefficient associated to the flutter. So I have W critical by this, the first pole here, the critical, by e to the power j omega critical by t plus the complex conjugated. I don't write. So I am including this pole as the first pole. Where is it? Okay. This is the first, this is the second, conjugated. Here we have the third, and the fourth here. So plus the third, plus the fourth, but these two are stable. Stable means that these two contributions will decay. I know, for any initial condition, because we have e to the power something negative by t. Okay? So the only part of the response that will survive in steady regime is the following. You should have okay, you should have equal, almost equal. I am neglecting the stable part. Neglecting the stable part, I have a coefficient by W, let me call flutter, please, instead of critical. Flutter eigenvector, e to the power j omega flutter t, plus the conjugated part. And that's it. That's it. In steady regime, okay? But, what happens when you sum a complex quantity to the complex conjugated? You will obtain the real part. Okay, so I can write the following. I can write the following. The time vector is equal, almost equal in steady regime, steady oscillatory regime, is equal to 2 times the real part, because a complex number plus a complex conjugated is equal to 2 times the real part. W tilde f vector, the famous critical eigenvector, e to the power j omega flutter t. Okay? And in component, we have 2 components because we have a vector. We have the constant is an essential. The constant is an essential. There is also a constant. I can put this constant here, and assuming that this constant is real. If you assume that this constant C1 is complex, this kind of demonstration is identical apart a phase shift in time. Okay? So please, don't care about the constant, please. And so we have, in component, we have the real part, 2 times the real part of the first, you have the flutter eigenvector, first component here, because, and here we have 2 real part of the flutter eigenvector, second component, and up we have e to the power j, j omega flutter t, and e to the power j omega flutter t. Okay, and so we have 2 components equal to I can 2C1 real part of. Now consider that is composed by a real part plus an imaginary part. This is a flutter vector, first component, a real part and imaginary part. Okay, first this is R for real and I for imaginary, and this is a J. Okay, so I'm talking about the first component of the critical eigenvector as decomposed in a real part and an imaginary part. We can do the same for this exponential. This exponential can be decomposed in a real part, which is the cosine of omega flutter by t, and j, the sine of omega flutter t. Okay, and that's all. The same real part for the second component. In fact, here we have written this quantity for the first component of the vector, real imaginary part, and we can rewrite the same for the second component. Identical quantity, but for the second component. Okay, W R plus J W, this is the critical eigenvector, so the flutter eigenvector, real part and imaginary part, by again cosine and J sine. Okay, now we have to take the real part of this product. The only way for obtaining a real part is multiplying this real part by this real part and this imaginary part by this imaginary part, considering the fact that j by j is equal to -1. Okay, therefore at the end we have 2C1, and here we have the W flutter 1 real part by cosine of omega flutter t, and minus the other portion of the real part is the product of the two imaginary parts. So we have W flutter 1 I for imaginary sine of omega flutter t. Okay, and this is the first component of this vector. The other component of this vector is with 2, so we have flutter 2 real cosine omega flutter t minus omega 2 imaginary flutter sine omega f t. Okay, now we can consider, we have here the real part and imaginary part of a complex number. Excuse me. Cioè c'è qualcuno che fa lezione da remoto, io se lo becco, ci fanno 2 gonadi così che dobbiamo fare tutte lezioni in presenza, e poi c'è qualcuno in facoltà che fa lezione, ma io adesso lo becco, lo denuncio al preside. Adesso appena ho finito quest'ora, tra qualche minuto, scappo di là e vedo chi è, perché non è possibile, cioè, che noi dopo tutto questo stress, scusate, sorry for English native people connected, but I am stirring something particularly deep for me. Excuse me. Okay, so I have the first, I have the first component, first, second, okay? We can write this in this special form. We can consider the module, the amplitude, the module as a module of a complex number of W1 flutter, and multiply this quantity by the imaginary part. This is a real part, sorry. This is a real part. By the real part of flutter, first quantity, divided by the module. I have put this in evidence, so we have a denominator. And this is multiplied by the cosine, omega flutter t, and minus the imaginary part of the first component, divided again this by the sine. And that's all. The same down here, we can collect this amplitude here, and then we have the real part of the flutter divided by the amplitude of the second component by the cosine omega flutter t minus the imaginary part of this flutter 2 by the amplitude by the sine. Okay, and what we see here, what you can see here, is the development of a Prostapherasis formula like cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. In fact, here you have a cosine of this angle, actually omega f by t, and the real part divided by the amplitude of a complex number is exactly the cosine of the phase angle of such a number. What I mean is the Pythagoras theorem, essentially. In fact, you have a complex number. This is a complex number, and you have the amplitude of the complex number, magnitude. You have, for example, zeta, complex number. This is the zeta modulus. This is zeta real part. Okay, and if you have this phase angle phi, zeta r on zeta modulus is the cosine of phi. So this is the cosine of the phase angle of WR by this. Okay? Okay, so we are finished because the conclusion is the following: W1t by W2t is equal to the amplitude of omega flutter first component by the cosine of omega flutter by t plus the phase of this number. And second component, we have omega flutter second component modulus cosine omega flutter t plus phi omega 2 flutter, omega flutter, yes, the phase of the number omega 2 flutter. And I have finished And what about the conclusion? Interesting conclusion. My original question was, what is the meaning? My original question, please don't do confusion between omega and W. My question was, what is the meaning of this? The flatter eigenvector, meaning. With a first component, a complex number, a second component, another number. For example, 2 plus j7 minus 3 minus j10. Two complex number. What is the meaning? Okay. The meaning is on the writing of the final. Let me a minute for writing this final formula before the break. This is the response of the system in flatter condition. Okay? We are in flatter condition, and this is the response. The response is equal to first, remember that the final formula is this. This is the final formula, guys. So you have to combine your mode of vibration with your time function. Remember. So, flatter condition, you have a combination of your time function, write in red, please, space function, excuse me, sine pi x by L, which is this function, by W1. But W1 is this. This is W1. So by, write together, apart an essential constant C1, we have the amplitude of W1, flatter, by cosine of omega flatter T plus the phase of the complex number W1 flatter. Plus the other shape function sine 2 pi x by L multiplied by our W2 time function, which is amplitude. Look, amplitude number 2, second component, by cosine of omega flatter T plus the phase of W2T. Okay, well, this is the other mode shape, like this. And so what about the conclusion? The conclusion is the following. Remember that our quantity to be analyzed are this green quantity here, this number, the and this number, module and phase, amplitude and phase in the second component, here and here. Okay, and you have the contribution. You have the contribution here for the first component, and here for the second component, So, first mode of vibration, first component, second mode of vibration, second component. The answer is the following. You are performing a couplet fluid structure interaction analysis, and you are using as base shape function the mode of vibration. The honest question is, how is the single contribution of the two structural mode of vibration? Can I quantify how much of this shape function is in the flutter vibration and how much of this other shape function is in our flutter equation. Another way for posing the question: if you don't have aerodynamic, you have separated mode of vibration, one like this and the other one like this. When you consider the couplet problem and you are in the margin of your stability, you should ask, in the critical flutter vibration, how much of the first mode is included in my response and how much of the second mode is included. This quantitative way for evaluating this influence is given by the component of the critical eigenvector. As component of the critical eigenvector, you have two complex numbers, and these two complex numbers in modulo and phase are giving to you the contribution of the first mode shape, namely the structural mode shape, and the second structural mode shape as contribution to the flutter analysis. This is exactly the same for an aircraft, complete aircraft flutter analysis. When you have a complete aircraft flutter analysis, you have the first mode of vibration of the aircraft, the second mode of vibration of the aircraft, and the third mode of vibration of the aircraft. In that case, your critical eigenvector is a complex vector with three complex numbers. These three complex numbers are given to you in modulo and phase the contribution of the structural mode of vibration to the critical flutter mode of vibration. Because essentially, with this expression here, this is namely the flutter mode. And the result of this analysis is that this shape here vibrating is the flutter mode. This is the mode including the structural and the aerodynamic contribution coupled. And this coupling is exactly described by this combination. And in this combination of the two structural shapes, you have two numbers weighting the contribution of the structural shape. These two complex numbers are the component of your critical eigenvector. So the critical eigenvector is an algebraic vector giving you the exact combination of your structural mode for obtaining the flutter mode. Okay, this is the conclusion of this first hour, and I have a break now. Okay, what about the response to the survey I gave you? 22 response. We have 9% of high-level expertise in model analysis, 60% on acceptable exercise, and sufficient exercise. Okay. So I can run. This is my conclusion. No. This eigenvector is actually 2 by 1. Oh, what is this? The SC vector, initial condition vector, is 4 by 1. Yes, it's 4 by 1. Yes. This is an answer to Valerio De Paulis.